In this problem, the Salle Robotics team is trying to elevate a robot at the end of a competition. The platform it's trying to reach is 3 meters above the ground. It's an 85 kilogram robot, and they're trying to select the right motor that would be able to produce the amount of power needed to move their robot in a period of time. Right, so we're thinking of power, we're thinking about the rate work is done. Right, so if I'm drawing a little picture, let's draw a little robot. It might have some wheels on it. Right, doesn't have to be too pretty here. And ultimately, we have a platform up above, and we're going to have some kind of winching mechanism that's going to come down to this robot. And we know that there is a 3 meter gap that we have to bring this robot up. Right, so ultimately, if we say this is position 1, well, later the robot is going to be elevated. Right, it's going to be up here, and that would be position 2. Right, so its energy has changed because there has been a force applied, right? It's been applied over a distance of 3 meters by some kind of winch or the motor that's going to be pulling that robot up to an elevation, right? So if we want to know the power is the amount of work done over a period of time. In this case, the work is done is lifting the robot. Right? So if we look at the energy at position 1, it has no energy other than stored energy in its battery. But at position 2, we have GPE. Right? So we go from 0 GPE down here to some amount of GPE at position 2. And we can't assume it. We can assume it gets to the top. It's not moving. So the change in energy, right? Remember, work is the change in energy over time. Right? Well, that change in energy is the work done by that motor. And that work done is the GPE at position 2, which would be the mass of the robot times gravity times the height at 2. Right? So we can calculate the work done, or the change in energy. Right? This would be the work. It's equal to that. And that's going to be the mass of the robot, 85 kilograms, times 9.8 meters per second squared, times the height of 3 meters, right? And that'd be kilogram meters squared per second squared. That is joules, right? And let's calculate 85 times 9.8 times 3. We have 2,499 joules. 2,499 joules of work needs to be done, right? There's a lot of motors that can do that amount of work, but there's a certain amount of power needed to do that in only 4 seconds, right? The power is the rate we do work. Right, so if we do that, we would take the work we do, 2,499 joules, and we would need to do that in only 4 seconds. Right, the amount of power output, therefore, if I divide by 4, is 624.75, 600, and let's just round it to 25 watts of power. Now they say, well, what's the power rating? And they say note horsepower. Well, sometimes when you go to the store, you are going to see a rating in horsepower, not in watts. Well, let's do a little quick conversion. We can just set up a fence post. The watts can be converted to horsepower. 1 horsepower is 746 watts. And now, so if I divide by 746, I find that I need a 0.84 horsepower, 0.84 horsepower motor, right? So if you're going to Lowe's or Home Depot and you're looking for a little electric motor that's going to connect to a winch, you might see that they have one that's a 0.25 or a 0.5 or a 0.75. Well, in this case, if I want this motor to be strong enough to lift this heavy robot, I might get myself a 1 horsepower motor, or maybe even a 1.5 horsepower motor, and know that I'll have plenty of power to spare for this robot.